Hello besties, how is everything going? This is part 2 of Matrices and Determinants series. In this part we are going to discuss types of matrices. Matrices are categorized based on their elements, orders and some other conditions. The following are the common matrices. The first type is a column matrix. A column matrix is a matrix with only one column but any number of rows. For example, number 5 inside the square bracket. It's a matrix having one element, one row and one column. The order of this matrix is 1 by 1 because it has one row and one column. It's a column matrix because it has only one column, which is a requirement for a matrix to be called column matrix. Second type, 0 and 2 arranged vertically and enclosed in a square bracket. This matrix has two rows and one column, so its order is 2 by 1. It's a column matrix because it has only one column. The third example is a matrix with an elements -3, 8, 10, root 6 and 20 arranged vertically in one column. It has 5 rows and one column, so its order is 5 by 1. What is common to all these three matrices is this one, which stands for the number of columns. For a matrix to be categorized as a column matrix, we shouldn't bother about the number of rows or the number or type of elements or any other parameters. What's expected from us is just to check whether that matrix has a single column or not. If it has a single column, that's called a column matrix, otherwise it's not. In general, a matrix with capital letter A is equal to small letter a sub ij with an order m by 1 is a column matrix of order m by 1. M, which stands for the total number of rows, can be any natural number. The second type of matrix is row matrix, which is a matrix with only one row but any number of columns. For example, number 2 inside a square bracket is a row matrix because it has only one row. By the way, it can also be a column matrix because it has only one column. Thus, a matrix with an order 1 by 1 can be considered as a row matrix as well as a column matrix. A matrix with elements 0.4, 6 and 9 arranged in a single row is a row matrix with an order 1 by 3. The third example is numbers and letters, that's root 10, z, 5 over 3 and 17 arranged in a single row and enclosed in a square bracket is a row matrix with an order 1 by 4. A matrix with 5 similar elements arranged in a single row is also a row matrix with an order 1 by 5. To categorize a given matrix as row matrix, what we have to check is the number of rows in that matrix. If the matrix has only one row, that's a row matrix, otherwise it's not. In general, a matrix B equal to B sub ij with an order 1 by n is a row matrix of order 1 by n. The third category of matrix is a square matrix. That's a matrix with the same number of rows and columns. In other words, if the total number of rows in a given matrix is equal to the total number of columns, that matrix is called a square matrix. The following are examples of square matrix. 0 enclosed in a square bracket. Number of rows is equal to number of columns, which is equal to 1. So this is a square matrix with an order 1 by 1. It can also be a row matrix as well as a column matrix. The other example, a matrix with an elements 1, c, square root of 5 and 30 arranged in 2 rows and 2 columns. Number of rows is equal to number of columns, which is equal to 2. So it's a square matrix with an order 2 by 2. This example also represents a square matrix with an order 4 by 4. To figure out whether a given matrix is a square matrix or not, just count the total number of rows and the total number of columns in the matrix and then equate them. If they are equal, that matrix is a square matrix. If not, it's not a square matrix, rather it's a rectangular matrix. Generally, matrix C is equal to small letter c with sub ij is a square matrix of order m by m. The fourth one is a diagonal matrix. It's a square matrix that has zeros everywhere except possibly the main diagonal. The main diagonal is a line that extends from the top left to the right bottom. For a matrix to be called diagonal matrix, it has to fulfill the following requirements. The first requirement, it should be a square matrix. That's the total number of rows have to be equal to the total number of columns. The second requirement, elements other than the main diagonal elements have to be 0. Main diagonal elements may or may not be equal to 0. Let's see the following examples. The first example is this 2 by 2 matrix with an elements of first row 1 and 0 and elements of second row 0 and 3. In this square matrix, elements as the main diagonal are 1 and 3. Elements other than the main diagonal are zeros, so it's a diagonal matrix. Second example, a 3 by 3 matrix with all elements equal to 0. It's a square matrix because the number of rows equal to the number of columns. Elements of the main diagonal are those connected by a line drawn from the top left 0 to the right bottom 0. For a matrix to be called a diagonal matrix, these main diagonal elements may or may not be equal to 0. In this case, all the three elements are zeros. Our center of attention is not on these zeros because these zeros are not a prerequisite for categorizing a matrix as diagonal matrix. Rather, those elements out of the main diagonal line. All elements out of the main diagonal line are zeros, thus it's a diagonal matrix. The third example is this 4 by 4 matrix. Main diagonal elements are those elements connected by a straight line drawn from row 3 to 4. Elements other than main diagonal elements are all zeros. Hence, this matrix is a diagonal matrix. In general, a matrix D is equal to small letter d with sub ij of order m by m is a diagonal matrix if and only if it is a square matrix and all elements out of the main diagonal line are zeros. Elements of the main diagonal can either be 0 or non-zero. The fifth category is a scalar matrix. It's a diagonal matrix where all elements of the main diagonal are equal. In case of diagonal matrix, we don't worry about the diagonal elements because these are not decisive factors for categorizing a matrix as diagonal matrix. But in case of a scalar matrix, these are the elements that determine whether a given diagonal matrix is scalar or not. Let's see some examples. This 3 by 3 matrix is a scalar matrix because it's a diagonal matrix having equal main diagonal elements. The same is true for this 4 by 4 matrix and 5 by 5 matrix. Generally, a matrix E is equal to E sub ij of order m by m is a scalar matrix of order m by m only when it's a diagonal matrix and all the main diagonal elements are equal. The sixth category is an identity matrix. It's a diagonal matrix where all elements of the main diagonal are ones. In other words, identity matrix is a square matrix where all main diagonal elements are ones and elements other than the main diagonal elements are zeros. These 3 by 3, 4 by 4 and 5 by 5 matrices are identity matrices because they are square matrices having 1 on their main diagonal and zeros outside the main diagonal. Generally, a matrix A is equal to A sub ij is an identity matrix only when it's a scalar matrix where all main diagonal elements are ones. From the other 4 definitions, we can figure out that identity matrix is a subset of scalar matrix, scalar matrix is a subset of diagonal matrix, and diagonal matrix is a subset of square matrix. In other words, an identity matrix is a scalar matrix. It can also be a diagonal matrix and also a square matrix. The other type of matrix is a lower triangular matrix. It's a square matrix whose elements above the main diagonal are all zeros. For example, let's analyze this 3 by 3 matrix. Elements on the main diagonal are ones. Our center of attention on such kind of matrix is elements above the main diagonal. We have these 3 elements above the main diagonal and all are 0. This matrix is a lower triangular matrix. The second example is this 4 by 4 matrix. As usual, our center of focus is on these 6 elements which are located above the main diagonal. They all are zeros. Hence, it's a lower triangular matrix. The third example is this 5 by 5 diagonal matrix. These 10 elements which are located above the main diagonal are all zeros. Thus, this matrix is a lower triangular matrix. In general, a matrix A is equal to A sub ij is a lower triangular matrix of order m by m only when all elements above the main diagonal are 0. The 8th category in our series is upper triangular matrix. It's a square matrix whose elements below the main diagonal are all zeros. In such kind of matrix, we are expected to check whether elements below the main diagonal are 0 or not. If they are 0, that matrix is an upper triangular matrix. If some or all are different from 0, that matrix is not an upper triangular matrix. For example, this square 3 by 3 matrix is an upper triangular matrix because all the 3 elements below the main diagonal are 0. By the same reason, this 4 by 4 matrix is an upper triangular matrix. This 5 by 5 diagonal matrix is also an upper triangular matrix because all the 10 elements below the main diagonal are zeros. Diagonal matrices are both upper triangular and lower triangular matrices because their elements above and below the main diagonal are zeros. Generally, A matrix A is equal to A sub ij with an order m by n is an upper triangular matrix only when all elements below the main diagonal are zeros. Whenever we are asked to check whether a matrix is an upper triangular or not, we have to check whether the elements below the main diagonal are zero or not. On the other hand, when we are asked to check whether a matrix is lower triangular or not, we have to check whether elements above the main diagonal are zero or not. The next matrix type is a zero matrix. It's a matrix with all elements zero. It can be a square matrix or rectangular matrix, but the necessary condition is that all the elements have to be zero. These 2 by 2, 4 by 3, and 4 by 5 matrices are examples of zero matrices because all elements of this matrix are zeros. Generally, a matrix B is equal to B sub ij of order m by n is a zero matrix only when all elements of the matrix are zeros. The 10th type of matrices are symmetric matrices. These are matrices that are symmetric along the main diagonal. In such type of matrix, the main diagonal acts as a mirror line because it acts in exactly the same way as a normal mirror does. For example, in this 2 by 2 matrix, this main diagonal line can be considered as a mirror line for this bottom zero because its mirror image is located at the same distance above the line. Let's analyze this 4 by 4 matrix. The main diagonal is a line drawn from this top left 0 to bottom right 1. If we examine each element below the main diagonal, we can find their mirror image above the main diagonal. This one is a mirror image of this one. This bottom left A has a mirror image of this top right. If we find a mirror image of this theta, we can find it here below the main diagonal. In general, elements on either side of the main diagonal have a mirror image on the other side of the main diagonal. So this matrix is symmetric matrix. This 3 by 3 identity matrix is also an example of symmetric matrix. The other type of matrix which is opposite to symmetric matrix is asymmetric matrix, which is a matrix that is not symmetric along the main diagonal. Unlike symmetric matrix, we can find the mirror image for each and every element on one side of the main diagonal. Let's see some examples. This 2 by 2 matrix is asymmetric matrix because we can't find the mirror image of this 0 and this 1. Also, this 4 by 4 matrix is an asymmetric matrix because this 5 doesn't have a mirror image on the other side of the main diagonal, and this 0 doesn't have a mirror image below the main diagonal. By the same analogy, this 3 by 3 matrix is an asymmetric matrix. All the above 11 matrices are rectangular matrices. You know why? As you remember, matrix is defined in part 1 of this installment as a rectangular array of numbers arranged in rows and columns. This means every matrix is rectangular from its very nature. Finally, let's see how to identify the category of a given matrix. The first matrix is this 5 by 5 matrix with zeros everywhere except the main diagonal elements. Definitely, this is not a row matrix or a column matrix because it has more than one row and one column. Is it a square matrix? The answer is yes, because the number of rows is equal to the number of columns. The other question, is it a diagonal matrix? Yes, it is, because it's a square matrix having zeros everywhere except the main diagonal. The third question, is it a scalar matrix? Also, the answer is yes, because it's a diagonal matrix having identical diagonal elements. The fourth question, is it an identity matrix? The answer is no, it's not, because the main diagonal elements are not 1. If all these are replaced by number 1, it will be an identity matrix. The other question, is it a lower triangular matrix? Yes, it is, because all elements above the main diagonal are zeros. Is it upper triangular matrix? Again, the answer is yes, because it's a square matrix having all elements below the main diagonal equal to 0. Is it a zero matrix? The answer is no, because the main diagonal elements are different from 0. Is it symmetric matrix? The answer is yes, because every element in the matrix has a mirror image on the other side of main diagonal. The second matrix is a 4 by 4 matrix with all elements 0 except the element at A sub 24 position. Is this a square matrix? The answer is yes, because number of rows is equal to number of columns. Is this a diagonal matrix? The answer is no, because among all non-diagonal elements, the one at A sub 24 position is different from 0. Since it is not a diagonal matrix, It can neither be a scalar matrix nor an identity matrix. Is it a lower triangular matrix? The answer is again no, because among all elements above the main diagonal, this 5 is different from 0. Is it an upper triangular matrix? The answer is yes, it is, because all elements below the main diagonal are zeros. Is it symmetric matrix? No, it's not, because this 5 doesn't have a mirror image below the main diagonal. It's not symmetric matrix means that it's an asymmetric matrix. Is it a zero matrix? The answer is no, it's not, because this 5 is different from 0. Thank you for your attention. By this, I conclude this section. Please subscribe, like, and share the page. Have a nice time.